As an example of using the relative gain array to pair manipulated and controlled variables in feedback control loops, let's consider again this inline blending operation, which has two manipulated variables, the flow rates of WA and WB, and two controlled variables, the total flow rate and the composition of the effluent. We'll call WA U1 and WB U2, and then we'll call W, the total flow rate, Y1, and the composition we'll call Y2. We already wrote the steady state total material balance and determined how the perturbations in W are affected by perturbations in WA and WB. For the component balance, we need to linearize the model equation using a first-order Taylor series expansion, which also converts the component balance to perturbation variable form. We can now write the steady state gains for each of the four process transfer functions. WA and WB are both related to the controlled variable W with a gain of 1, and WA and WB are related to the controlled variable XA with the gains shown here. Example 18.3 from our text shows that WB bar over WA bar plus WB bar squared is equal to 1 minus X bar over W bar, and that minus WA bar over WA bar plus WB bar squared is equal to minus X bar over W bar. These come from the steady state component balances, assuming that WA is a mass flow rate of pure component A. The relative gain, lambda 1,1, relating changes in the flow rate W to changes in the flow rate WA can be computed using the formula that we introduced earlier, which gives us X. Now we can compute the remaining relative gains, lambda 1,2, lambda 2,1, and lambda 2,2. Since X is a mass fraction, it must be between 0 and 1. If X is large, then we would want to use the 1,1, 2,2 pairing, and if X is small or close to 0, then we would want to use the 1, 2, 2, 1 pairing. The relative gain analysis may show that there is no optimal pairing or that the best pairing has problems because one of the control loops oscillates, for example. In this case, we may want to use an advanced control strategy called decoupling control. Decoupling control uses controllers designed to decouple the interactions between the control loops. Earlier, we introduced a block diagram for the 1-1-2-2 pairing. This block diagram is a modification of that 1-1-2-2 pairing containing decoupling controllers in the transfer function blocks T21 and T12. T12 and T21 are feed-forward controllers designed to cancel the effects of GP12 and GP21 on the respective controlled variables Y1 and Y2. When designing these two feed-forward controllers, we consider the manipulated variable U2 to be a disturbance to the controlled variable Y1, and we consider the manipulated variable U1 to be a disturbance to the controlled variable Y2. Because U1 is manipulated, we know exactly what it should be based on the signal coming out of the controller GC1. That known disturbance can then be fed into a feed-forward controller, which modifies U2 to account for the disturbance that will come in U1. Similarly, U2 is a controlled variable, so its deviations are also predictable based on the signal coming out of controller 2. Being able to predict deviations in U2 enables us to design a feed-forward controller that manipulates U1 in order to account for the known disturbances that will come in U2. How should these two feed-forward controllers be designed? They should be designed so as to eliminate the undesired effects of the manipulated variables U1 and U2 on controlled variables Y2 and Y1. T21 then should be designed as minus GP21 divided by GP22, and T12 should be designed as minus GP12 over GP11. We saw in Chapter 15 that feed-forward controllers are often designed as lead-lag elements, and we also saw that sometimes the ideal feed-forward controller is not physically realizable. For example, if GP21 is a lower order transfer function than GP22, then T21 would have higher order terms of S in its numerator than in its denominator, which is not physically realizable. We can also design these feed-forward controllers based on static considerations. In this case, we use only the steady-state gains from the transfer functions to design the controllers T21 and T12.